Good afternoon. Today I'm presenting on Mullite, a high-temperature engineering ceramic known for its excellent thermal shock resistance. We'll cover its raw materials, crystal structure, key properties, processing steps, and focus on the creation of a specific finished product, a Mullite kill setter plate. Mullite, thermal shock resistance, and refractory applications. Let's begin with the raw materials. Mullite is made from natural materials such as kaolin clay, kyanite, andalusite, or combinations of bauxite and silica. You can see the raw mineral lumps and crystalline forms here. These materials are mined from natural deposits, then crushed and ground into fine white powder, shown on the right. This powder is the starting point for all Mullite ceramics. This is the crystal structure and microstructure of Mullite. Mullite has an orthorhombic crystal structure built around chains of aluminum oxide octahedra. The most important feature develops during processing. Long, needle-like Mullite crystals grow and interlock with each other. This network of interlocking needles is what gives Mullite its strength and outstanding ability to resist cracking when temperatures change quickly. Mullite has several key properties. Thanks to its crystal structure, Mullite has several outstanding properties. It has a very low thermal expansion coefficient, which means it doesn't change size much when it's heated or cooled. This gives excellent thermal shock resistance. Mullite can survive rapid temperature changes without breaking. It also has a high melting point, around 1,840 degrees Celsius. Mullite resists creeping under load at high temperatures. It stays chemically stable and has low thermal conductivity. Here are the main manufacturing steps for Mullite ceramics. First, the raw minerals are mined and refined into fine powder. Then we carefully batch and mix them with alumina or silica to reach a 3:2 ratio. The powder is formed using dry pressing or extrusion, dried to remove moisture, and finally sintered at very high temperatures between 1,400 and 1,700 degrees Celsius. During this sintering step, the Mullite crystals form through a solid state reaction and create the strong interlocking structure. After sintering, Mullite turns into dense, strong, white, refractory ceramic parts. Here you can see examples of finished forms such as plates, tubes, rings, and complex supports. These components are designed to handle extreme heat and repeated thermal cycling in industrial environments. Now, let's look at a specific finished product, the Mollite kiln setter plate. These thin, flat plates are used in industrial kilns to support other ceramic wares while they're being fired at high temperatures. The plate must remain perfectly flat and strong even after many heating and cooling cycles. It must withstand repeated high temperature cycles without cracking or deforming. This is important because other types of ceramics have to be heated to temperatures in order to harden them. And they must be on a surface that will not cause them to crack or break. Manufacturing a Mollite kiln setter plate starts with raw powder preparation and precise batching using kaolin and alumina sources. The powder is mixed thoroughly and then formed into the plate shape by dry pressing. After drying to remove any remaining water, the critical step is high temperature sintering at around 1500 to 1600 degrees Celsius. At this temperature, Mollite crystals grow and interlock, turning the pressed powder into a dense, strong, thermally stable ceramic plate ready for use in industrial kilns. In conclusion, Mollite's low thermal expansion, combined with its interlocking, needle-like crystal structure, gives it exceptional thermal shock resistance. Through careful processing, especially the high temperature sintering step, Mollite becomes an ideal material for demanding high temperature applications such as kiln furniture. It is a versatile engineering ceramic that performs reliably where many other materials would fail.